How y'all doing? Today we're going to be talking about buffers in the context of acid-base chemistry. Now, first things first, I want you all to consider what pH and pOH is, and how that tells us how acidic or basic a solution is. Now, as far as buffers go, buffers are going to be substances that resist a pH change when an acid or base is added to solution. Now, in the real world, some examples of buffers are going to be blood or a lot of other biological systems, because having a balanced pH within that system is super important. So let's go ahead and get started. A buffer, once again, a buffer is going to be a substance that resists a pH change. Once again, it's a substance that resists a pH change, and every single buffer that we're going to be looking at is composed of a weak acid and its conjugate base. It's conjugate, or vice versa, weak base and its conjugate acid. Now, the reason that this is important is because these substances will not react with each other. They exist, remember, in equilibrium. So a weak acid and its conjugate base, or a weak base and its conjugate acid, can exist both in the same solution together. So how do these work? How do buffers work? Well, basically, they act in neutralization reactions. They act in those acid-base reaction, neutralization reactions. And when we're looking at them, any added acid will react with the existing base, and any base added will react with the existing acid. So, and once again, if you add a base, the base, which will be the OH here, will react with the acid, making liquid water, H2O, and the conjugate anion just stays in solution. And vice versa, if we go ahead and add an acid, the acid will react, adding the hydrogen ion, will react with the conjugate base that's in solution, reforming the conjugate the conjugate acid to that conjugate base, which is just the weak acid itself, and vice versa. So once again, if I have all of the acid and its conjugate base in solution at the same time, they're not reacting with each other in a neutralization reaction. However, any separate added base or acid will react with each one of those things respectively. All right, so moving on, it is very important for us to understand what the pH of a buffer solution is. And you can totally use an ice table to determine this. However, there's actually a really nice, straightforward reaction, which is listed and provided for you on the AP sheet, and it's the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is the following: pH is equal to the pKa plus the log of the base, the concentration of the base, divided by the concentration of the acid. Now, once again, this is provided for us. However, if we are looking at a solution that is a base and its conjugate acid, the pOH cannot be determined directly from that, but rather the pOH can be determined from that. This is not provided for you, but it's a good one to have on the back of your mind. It's pretty much exactly opposite of everything I wrote up above. The pOH is equal to the pKb, the base dissociation constant, plus the log of the concentration of the acid over the base. And once again, if you know the top one, which it is provided for you, the bottom one, which is not provided, is just opposite. Not provided. So once again, these equations are super useful because if you can recognize that you have a buffered solution, which is once again always a acid and its conjugate base or vice versa, you can determine the pH of that solution given the Ka, the concentration of the conjugate base, and the concentration of the acid. So let's go ahead and try it out. What is the pH of a buffer solution that is 0.12 molar lactic acid and 0.1 molar sodium lactate? The Ka for lactic acid is 1.4 times 10 to the negative fourth. So when we're looking at this, we know that lactic acid is some sort of weak acid. It will react with water and form an equilibrium where we have and form H3O. And the conjugate, which would be lactate, the Ka for this is going to be 1.4 times 10 to the negative fourth. So first things first, we know that because this is a buffer solution, because it's stated in the problem, but also because I have lactic acid, a weak acid, and sodium lactate, its conjugate base, we can go ahead and determine the value of the pH. And the pH is as follows. pH is equal to the negative log of 1.4 times 10 to the negative fourth plus the logarithm of the concentration of the base over the acid. Once again, we have lactic acid, which is a weak acid, and its conjugate base, sodium lactate. So this is going to be 0.10, that's the base, divided by 0.12, which is the concentration of the acid. And I'll go ahead and give you a second or two to punch this into your calculator and see if you can determine the pH of this mixture. So after punching in our calculator and determining that we have a buffer solution, we use the Henderson-Hasselbalch equation, and we find, hopefully, that the pH of this mixture is 3.77. Excellent. All right, so moving on. It's important to know what makes a good buffered solution. And the way we determine this is using buffer capacity. And hopefully, based on what we know about the word capacity, it's basically telling us how much acid or base can be put into the solution before the pH does change dramatically. So, for example, if I had a little bit of acid or base into distilled water, the pH will drastically change because water is not a buffered solution. However, if I add a little bit of acid or base to a buffer, depending on how good the buffer is, the pH may or may not change. So once again, the buffer capacity refers to essentially the amount of acid or base the buffer can neutralize of acid or base. The buffer can neutralize before the pH changes considerably. The pH changes considerably. And once again, this is basically just saying how good is my buffer. The higher the concentration, obviously, of the weak acid and the conjugate, the higher the buffer capacity. The higher the concentration of the substances within the buffer, the better the buffer is. So the higher concentration of the weak acid and conjugate base, the greater the capacity. And last but not least, we want to, as scientists, identify what a good buffer would be. So not only will it be able to neutralize a lot of acid or base that's added to the solution, but we also want to keep certain buffers around certain ranges. So the way we identify this is that a good buffer will have a pKa value near the desired pH. So the closer the negative log of the Ka value is to the desired pH, the more likely that will be an appropriate buffer solution to use. All right, so last but not least, in this section, we're going to be looking at how to calculate um, the solution of a buffer solution after adding acid or base to it. And the way we're going to do this is we're going to be using before and after tables. So once again, I want to remind everyone that when I add an acid or base to a buffered solution, the first thing that's going to happen is a neutralization reaction. So once again, neutralization between buffer and added acid or base occur to completion. Now, as far as this goes, this is going to be a stoichiometry type problem. There is no equilibrium, so we need to consider first stoichiometry. When this when a neutralization reaction occurs, the result is often still a buffered solution. So once again, a buffered solution may result from a neutralization reaction. What this essentially will look like is when you, let's say, take a weak acid and begin to neutralize it with a strong base. When you do this, you're creating the conjugate base of the weak acid in solution. And if you have an appreciable amount of the weak acid and its conjugate base, you still have a buffered solution. Last but not least, and I'll go show you an example of this before-after table in just a second. The before-after tables we're going to be using to indicate a limiting reactant problem. And so these neutralization reactions, once again, we have to identify what runs out first. So we use the before and after tables, the BA tables, kind of like ice tables. They're not, I'll show you the difference between them. Show what chemical or chemicals remain. And what do we call this type of substance? A limiting reactant problem. So before after tables, once again, help us identify what substance is remaining. To kind of warm us up here, I have three chemical reactions. These are all neutralization reactions. The first two are like the classic metal hydroxide reacting with the acid, and the last one is going to be a Bronsted-Lowry reaction. Give you a few seconds to work on those. So for the first reaction, we have sodium hydroxide reacting with acetic acid. The first product, if you will, would be sodium acetate. And the second product would be water, where the hydrogen and the hydroxide pair up to form the water. The sodium and the acetate form the sodium acetate. The second product is going to be potassium cyanide, KCN, and water. And then the last reaction, what essentially happens is the hydrochloric acid, which is a strong acid, gives its proton to the acetate anion. Excuse me, this is not acetate. This looks like C6. H5O. This looks like phenol to make HC6H5O plus the chloride ion. So these are going to be the three reactions here, and hopefully you can identify that when the hydrogen ion is added from a strong acid, it will automatically get put onto the anion. And as far as the hydroxide goes, it will do something very similar to the cations. All right, so let's try this out. What we're going to do here is we're going to look at a neutralization reaction creating a buffered solution. So since we know it's going to be a buffered solution, we know at one point we're going to be using the Henderson-Hasselbalch equation. But first, we need to identify what chemicals reacted and how much of something I have left over. And this is where the before after table is going to come into play. So let's go ahead and check it out. A buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate, so acetic acid, sodium acetate, to enough water to make a 1 liter solution. The pH of the buffer is 4.74. What is the pH when 5 milliliters of 4 molar NaOH is added? So the first thing I want us all to realize is that when we're looking at this equation, we want to figure out what the pKa of the acetic acid is. And the way we're going to do this is by using the Henderson-Hasselbalch. The Henderson-Hasselbalch, once again, is pH is equal to pKa plus the log of the base over the acid. So the pH of the buffer prior to adding any base was 4.74 pKa plus the log of, it looks like it's going to be 0.3 molar over 0.3 molar. I'll go ahead and write that out, but hopefully you go ahead and see that this is going to be 1. And the log of 1 is going to be 0. So right now we have the fact that 4.74 is equal to the pKa. By taking the anti-log of this value here, remember P is the negative log, we find that the Ka of acetic acid is going to be 1.8 times 10 to the negative 5th. I'm going to leave both of these values up because we might need one or the other, depending on the context of this problem. Moving on, we know that we're going to add 5 milliliters of 4 molar NaOH. Now, hopefully you have memorized NaOH is one of the strong bases, So when I add NaOH into this solution, is it going to react with the acid or the base? And hopefully you recognize that it being a base, we will react this with the acetic acid. So this is going to be HC2H3O2. Now, this being a acid-base reaction, this is going to happen to completion. So we're going to form sodium acetate, C2H3O2, and water. We're going to use our before-after table. Now, once again, with our before-after table is going to be a limiting reactant type problem. So in this table, we can go ahead and add moles of everything. This is different from an ice table because remember, in an ice table, I'm only allowed to add molarity or partial pressure. Before and after tables, you're only allowed to add moles. So the moles of NaOH is going to be 0.005 times 4, giving us 0.02 moles. And as far as the HC2H3O2 goes, we're going to find that the number of moles is going to be 0.3. Sodium acetate is also 0.3. This is going to be our conjugate base to the acetic acid. And water is present, but we'll just say for right now that the initial concentration of water was 0. Now, when this reaction occurs, I have 0.02 moles of NaOH and 0.3 moles of HC2H3O2. Which one of these chemicals will run out first? The base. After this reaction runs to completion, I have no more sodium hydroxide. I have slightly less amount of acetic acid. I have 0.28. I formed 0.02 moles of sodium acetate, and I formed 0.02 moles of water. But once again, this is all happening in water, so this last step isn't necessarily important. And wouldn't you know it, I have an amount of sodium acetate and acetic acid, sodium acetate and acetic acid in solution. This is still a buffered solution. So what I can go ahead and do is I can actually use the Henderson-Hasselbalch one more time. By taking everything that I found from either the beginning or the end, I can find the pH of the resulting solution. So pH is going to equal to 4.74 plus the log of the concentration of the base over the acid. Now, the last cool thing about Henderson-Hasselbalch is that because buffered solutions are often going to be in the same container, the volumes of these substances are going to be the same. So I can actually take the moles that I found in the before-after table and use them in the Henderson-Hasselbalch, even though it's asking for the concentration. And that's because, once again, the volume of each of these are the same. So essentially, they would cancel out. After doing all this math, we find that the pH of the resulting solution is going to be 4.80. And this totally makes sense because by adding a base to a solution, it will increase the pH of the solution, not by very much. Notice that it's by 0.06. And that's good because we do not want buffer solutions to change pH when a acid or base is added to the solution. There's one more question down below. I want you guys to try it out yourself. The solution is posted online. Thanks a lot. See you next time.